I welcome everybody in the audience. I will be very brief, so we will have a webinar that will last for 2 hours. We will have basically 3 parts. The first part will be a presentation of global policy about hydrogen development, both in UK and in France. Then after, we will move to some more technical consideration. And then we will have a last but not least, as usual, as we say, presentation that will give us a hint of what Europe and the European Commission is up to in matters of hydrogen. And also there will be a focus on this presentation about transportation, which is very important. So without further ado, I will now hand the floor to Professor Jim MacDonald. I will briefly introduce him. He's the Principal and Vice Chancellor of the University of Strathclyde, and I apologize for my pronunciation in advance. And also, he co-chairs the Scottish Environment Energy Advisory Board, and he had in his past numerous high-level positions, whether at laboratories or energy catapult system. So we are very happy to have him today. And Professor MacDonald, the floor is yours.
Thank you very much, Paul-Yves. And I should say the main reason I'm here today is that I'm President of the Royal Academy of Engineering. So I look forward to sharing some of the work that's been done by the Academy. So good morning, colleagues. I should also say I'm an electrical engineer, so I'll try and give you some perspectives from an engineering systems view. So you can see from my presentation, I want to give you some broad background to what the Royal Academy of Engineering would propose as essential for the development of the energy infrastructure and indeed the energy futures. And we would propose an energy systems strategy. Thank you, Ludovic. To the next slide. So let me just qualify what I'm going to say in terms of a rather impactful communication that was given to Mr. Johnson, our Prime Minister, in February last year. The Council for Science and Technology is the Prime Minister's independent group that reviews science, engineering, technology and innovation. And we took on a significant piece of work proposing a systems approach to net zero with a very large group of engineers, technologists, policymakers, and submitted the report, which is public. You can find this on the government website, suggesting how the UK government might take a disciplined and I would say an engineering approach to whole systems, and Paul Jordan may refer to this approach as well. Without unpacking the whole letter, I would commend you have a look at it. The key recommendations were that we had a cross-government approach. As we know, net zero is a massive challenge. It is an absolute necessity, but we need that cross-government coordination and engagement with, of course, the investment community, engineering, technology, and indeed citizens. So the complexities, the interdependencies were key, but the key thing here is leadership and building a clear vision of the system that's required to achieve net zero. And I'll say something about that in a moment, but looking at low regret options, what 2050 should look like. And again, the Energy Systems Catapult have done some excellent work on doing that. But also recommendation 2 was about creating a multidisciplinary operational group. Many of you know in engaging with government, the danger is you can take a very good idea and it drops into a silo architecture. And whilst the idea is important, it may not get the traction and it may not get the multidisciplinary, multi-departmental attention it needs. And of course, systems expertise is key. The Royal Academy of Engineering has been working closely with government for the past 18 months, introducing and effectively doing some knowledge exchange on how systems approaches might be taken. And the third recommendation, and as an engineer, this is important to me, is underpinning all of this with strong analysis, engineering and technology principles, and providing ministers in the operational group with key evidence and data. And modelling and simulation is key in all of that. But of course, we also have to accelerate and demonstrate at high levels of late stage R&D how many of these technologies work. I'll come on to that in a moment. Thank you, Ludovic. So the Royal Academy of Engineering has put together a significant group that is advising on taking a systems approach to net zero. The document you see referred here is the strategy for the Royal Academy of Engineering. It's built around two pillars, a global sustainability and an inclusive economy. But around net zero, the three themes that we're driving is to build awareness of the value of systems approaches. It can be rather ephemeral if you don't describe what this means, but there's a strong body of theory, strong body of evidence in the application, where it's from aerospace, where it's from energy, where it's from the manufacturing. Systems engineering works on large, complex problems where you need to understand interdependencies, synergies, and for the journey in hydrogen in particular as an energy vector, we need to understand how that would fit into an overarching energy systems strategy and architecture. The second theme is supporting government in operationalising these systems approaches. So as we know, we have less than 1,600 weeks to 2050, so we really need to accelerate our understanding and de-risking of infrastructure evolution, decarbonising, whether it's transport, energy production, use, and in so doing, with that systems perspective, communicating clearly with society as to how behaviours and the benefits of a net zero architecture, what that means for them. And the third theme is providing insights and other engineering-based advice. Thank you, Ludovic. You will have these slides after the presentation. Have a look at these presentations, please. You can find it from the Royal Academy of Engineering website, where there's a detailed proposition around the systems perspective on climate change, where we build up systems mapping, understanding the technical detail, but understanding how technology, policy, economics, and society engage to come forward with the solutions and the directions of travel to achieve the net zero architecture that we need. And of course, with the experience we've had over the past year, this drive towards net zero means that we can also drive an economic recovery that creates industries, opportunities, and new architectures as we make the many tens to hundreds of billions of pounds of investment we need. Let's create, as my friend and colleague Lord Nick Stern said 15 years ago, the economics of climate change. As we move towards this, whether it's hydrogen, offshore energy, smart grid, electrification of transport, let's build economic opportunity as we do that. So another systems perspective, what is the economic dimension to these multi-dimensional challenges? And you can see some of the information graphics that you can pick up on the Academy's website around net zero by 2050 and giving you an engineering roadmap to 2050. Thank you, Ludovic. So back to this policy interaction on building the awareness of the values of systems approaches. Myself and the team at the Royal Academy have been spending a lot of time over the past year to 18 months with the senior government officials in the UK, permanent secretaries, indeed engaging with the Cabinet Office themselves. Number 10 directly, Mr. Johnson has warmly welcomed the Royal Academy of Engineering's input and responded very positively to the Council for Science and Technology's recommendations. The Government Office for Science and BEIS, and as we talk about this journey being a move towards COP26, I'm pleased in my home city of Glasgow. Let's hope everything goes as well as we hope. We've been trying to feed in evidence and pointers to really use November of this year as an accelerator to move towards 2050 and net zero. Okay, Ludovic. I will go through the next few slides rather quickly. We have to identify low regrets options, and we can do that by modelling and simulation and the argument about where the key existing technologies might be that require to be integrated, where the options might be that are emerging, and then move towards large-scale demonstration, de-risking, and then deployment. And that is key. We've been having these discussions for many years. Over the next decade in particular, we really need to see the infrastructure changing, the energy systems evolving quickly, and hydrogen will be a key part of that, I have no doubt. Thank you, Ludovic. And here's an idea. I'm going to give you two very brief looks at what we're talking about. Taking the systems approach means you do that systems mapping. You look at the multidimensionality of the problem so as to understand where the key pinch points are to achieve a particular outcome. These insights are key, where in this case, the challenge was decarbonising homes. Proposition here, as you can see in the top right hand of this slide, is where does hydrogen fit in on that in terms of transport, the production infrastructure, how that engages with other technologies to give that whole systems approach. But in so doing, we can identify where government has to play a role for key interventions. Be that national, devolved, or local government area, where the investment opportunities have to be, where the infrastructure has to be evolved, and quite frankly, where the engineering and technology can make a difference in achieving this. Thanks, Ludovic. And just directly to the point for this morning, and then I'll come to a conclusion over the next few minutes. The role of hydrogen in achieving net zero is key. The Royal Academy of Engineering has already made a contribution to the House of Commons Science and Technology Committee. Again, that would be available for you to review. This was done in January this year, providing some direct insights. And the key messages from the Academy's Net Zero Working Group is that there are multiple possible pathways and endpoints. Well, we understand that. The diagram in the bottom right hand of the corner again is a systems map demonstrating where the interdependencies and where the synergies lie. And of course, within each of these blocks, there's a significant challenge technologically in terms of creating the infrastructure and looking at how the system might evolve around other parts of the system. So having that vision for 2050 and then making these low regrets options to demonstrate, prove, and then expand upon investment in infrastructure is key. So systems thinking and clear decision-making frameworks are essential. That's why I would always propose a systems engineering approach. It's structured, it's underpinned by good methods, it's evidence-based, and this is what we need to do now to inform and support the policymakers and the investors. So again, we can come back to this later in questions if necessary. Thank you, Ludovic. So let me come to the Scottish Government hydrogen policy priorities. I chair with the First Minister of Scotland the Government's Energy Advisory Board, and we're about to, in the next few months, publish the hydrogen policy priorities for Scotland. If we go to the next slide, none of this will surprise the experts on this call from hydrogen, but the key objective for Scotland is to achieve net zero by 2045. And the Committee on Climate Change gave some good insights as to why Scotland can bring forward the targets for net zero and also in that stepping stone, because we can't leave it too late to achieve these targets. We have to have very credible near-term goals as a stepping stone towards this. 2030 is key. And our Prime Minister, Mr. Johnson, his 10-point plan for a green industrial revolution gave some very encouraging insights to where he would like to see hydrogen playing its part by getting to 5 gigawatts of hydrogen by 2030. And in Scotland, we're now moving towards renewable or low carbon heating, major investments from 2024, decarbonisation of cars and delivery vehicles by 2032. And these targets are important. As an engineer, I'll need to see plans, I need to see delivery points, and if we can't measure it, we can't control and deliver it. So the key thing here is we believe in Scotland, as does the UK government, of course, that hydrogen can absolutely be a key vector in the net zero journey. Thank you, Ludovic. This is a very extensive piece of work in the hydrogen assessment report. You'll see a link on this slide that you can look at post this meeting, initiated in February last year, completed quite recently, and looking how assessment can fit in the overarching Scottish energy system, which of course is nested within the UK system and beyond that into the overarching energy architecture of Europe. Thanks, Ludovic. And the policy statement is emerging. We have a clear ambition as well in Scotland that resonates with Mr. Johnson's plan for the UK. As it happens, Scotland is proposing it can produce 5 gigawatts of installed hydrogen by 2030, which is all of what Mr. Johnson is planning for the UK. So we could perhaps even increase the investment and targets of the First Minister and the Prime Minister, committing £100 million worth of funding. And as you can see on this graphic, taking a systems perspective, because effectively this is what we're looking at, from production transportation and utilisation, and how that engages and interacts with the electricity system, with transport system as well. And the final couple of slides, thank you, Ludovic. Having a look at some Scottish examples, and again, here is a microcosm of a system within hydrogen playing a key part. And this is the Orkney Islands, where you can see there are community wind turbines that are doing the electrolysing process of hydrogen production. It's then taken through a storage system, brought onto the main land of that island system, and then used for the driving of vehicles on the island. So again, a small but very meaningful project. And this is what I mean by getting to meaningful demonstration, taking a systems perspective and getting public and private sector support. Next slide, please, Ludovic. And of course, as we know, oil and gas industry are committed to their journey for energy transition and understanding how we articulate blue and green hydrogen. And there are some major projects that I won't talk about just now in the northeast of Scotland, where the oil and gas industry are now looking to use a mixture of carbon capture and storage and large reforming strategies to crack the hydrogen out of the product of the North Sea oil fields. So again, proving at scale and giving us a basis in which to build a whole industry. And my last slide simply captures the essence of where Scotland is going. The Hydrogen Action Plan will be published in 21, undoubtedly post the Scottish election, and I am confident that in partnership between the Scottish and UK governments, and very importantly with industry backing, we can move towards that systems approach to design, de-risking, but acceleration and proving of scale. And of course, I believe hydrogen will have an important part to play in an overarching decarbonised energy system. Thank you.
Well, thank you, Professor MacDonald. It was very interesting presentation, and especially the work by the Royal Academy and Engineering, and also the articulation about what UK is putting forward, like the 10-point plan and the Scottish plan. It is sure that Scotland, with this very powerful oil and gas industry, has some remarkable asset, I think, to play for hydrogen. I will just tell all the participants and the audience that if you have any question, either for Professor MacDonald or for all the other participants, the other presenter, can you use the functionality that we have in Teams and write those questions? I will take note, and of course I will put the question forward to all the participants, and I will have my own question also. So we'll do all the slides, presentation, and after we'll have a Q&A session, if that's okay for you. So write your question, please. Thank you again, Professor MacDonald. I turn the floor now to Philippe Boucly. Good morning, sir. Bonjour, monsieur.
Bonjour, good morning.
Voilà. So Philippe Boucly is the president of France Hydrogen. France Hydrogen is an association that coordinates the action of all the players, the company, the research center, the local authority involved in hydrogen and fuel cell sector in France. So France Hydrogen has really a key role in France for the implementation of the recently made public plan for hydrogen development in France. Before having this position, Philippe Boucly had a long and distinguished career, mostly in the gas industry, through the main French actors like GRT Gas and also GDF Suez. So, Mr. Boucly, the floor is yours, and we are longing to hear about what is the French plant and what is the role of the important role of your association France Hydrogen into this fresh France plan. Thank you in advance. The floor is yours, Monsieur Boucly. À vous.
Thank you. Maybe you can put the first slide. Yeah. So good morning, everybody. We are really at the dawn of a new era. So I will present shortly what are the challenges where we are in the implementation of the French strategy and what are the challenges in front of us. So next. I will jump immediately to the presentation of the French hydrogen strategy, which was published on the 8th of September last year. So three priorities. The first one, there is no order between these priorities. The first one is to decarbonize industry. It's a it's a means to scale up rapidly and to create a competitive French electrolysis industry. The second priority would be to develop hydrogen for professional mobility. What I call professional mobility is heavy-duty mobility and also what we could call intensive mobility, taxis or last-mile vans, etc. Last-mile mobility. So it's about vans, buses, trucks, railway, ships, and maybe a little bit later, airplanes. I will come back later about the support to this all these priorities. And the third priority is to continue to develop research and development and innovation. There is we consider that research centers in France are at the top of the research in the world. So the means of this priority is to maintain this high excellence level. In total, the French government is prepared to allocate 7.2 billion euro up to 2030, with a strong wish to go rapidly, so to engage 3.4 billion euro before 2023, and among these 3.4, 2 billion before the end of 22. It would result in installation of 6.5 gigawatt by 2030 for producing 600,000 tons of hydrogen, of low carbon and renewable hydrogen. And in terms of jobs, creation of between 50,000 and 150,000 jobs. Of course, they will be developed within the European strategy for hydrogen. Next, please. This strategy was published on the 8th of July last year, and the target is to produce 10 million tons of hydrogen by 2030, with the installation of 40 gigawatt in Europe and 40 gigawatt outside of Europe, for instance, in Ukraine or North Africa. There is a governance which is for governing this the implementation of this strategy. It's a so-called Clean Hydrogen Alliance, made of CEO of large groups and commissioners, in order to monitor how this strategy is implemented, and of course their decision will be fed by the work of 6 roundtables, which are along the full value chain of hydrogen. Of course, this similarly to France, this strategy is included within the Green Deal and the recovery plan of Europe, and efforts are presently deployed in order to install hydrogen within an IPCEI, which is the acronym for Important Project of Common European Interest. It's to do with hydrogen. What was done with the batteries means this would allow European government to national government to help their champions more easily within the framework of the International Trade Organization. Next, please. So to be more precise about the financial support of the French government, so this will be for national project, this will be done through call for projects. This call for project will be managed by ADEME. ADEME is a French agency for environment. So two main call for projects, one for developing technological bricks and demonstrators with 350 million euros, and another one for developing a territorial ecosystem with the strong objective to mix all the usages, so basically industry and mobility, in line with the national strategy. So for that, 275 million euros. And the second part would be also what will be done within this important project of common European interest with 1.5 billion euro, which would, for instance, which would be allocated for developing gigafactories of electrolyzers. No, not yet. There will be also a support mechanism because, as you know, the green or blue hydrogen is more expensive than gray hydrogen. So to fill the gap between both, we need some support mechanism which will fill this gap, and specifically for refineries, where the tax regime is specific, there will be also a specific mechanism. Thank you. Next. So 6 months after the publication of this strategy, where are we? If we consider all the projects which were published, either within the IPCEI, so mainly decarbonization project within the industry, or within the call for project of ADEME. In total, there is an identified electrolyzer capacity of 3,200 megawatt, 3.2 gigawatt. So we are halfway, I would say. And so we can be confident about the development of this strategy. And to feed this project, there are already some projects of gigafactories of electrolyzers, actually 3 or 4. One in the field of alkaline electrolyzers, there are 3 projects which would create gigafactories by 2022, 24, and 27. And also a very promising technology, the solid oxide high temperature electrolyzers, with a project which is led by Schlumberger with the CEA, and also with cement producer, Vicat, and also the region of Occitanie, and also with Vinci. So big groups and CEA in order to promote, to develop this new, very promising technology. And we can mention also this partnership between Siemens and Air Liquide, Siemens, which is strongly involved in PEM electrolyzers. Next. So, what are the challenges for the French hydrogen sector now? 3 challenges: to promote technological neutrality, to scale up in order to reduce costs, because I would say the main obstacle is still the cost, and to contribute to the reindustrialization of France. Next. As far as technological neutrality is concerned, it's not only about renewable electricity. It's possible to produce low carbon hydrogen using other means, for instance, electricity coming from the French mix, which is strongly decarbonized and which allow France to produce hydrogen at a very low content of CO2. And it is not only about electrolysis, there are other means to produce a low carbon or renewable hydrogen. I mentioned here the three means. So to combine CCS, capture and sequestration or utilization of CO2 with steam methane reforming, or to use the thermolysis or the pyrogasification of biomass in order to produce hydrogen. What is at stake by 2050 is to be able to produce enough renewable hydrogen. And to know that, we have launched a study to see if there will be enough renewable hydrogen, to assess the balance between supply and usages by this horizon. So it will include all the efficiency efforts which could be made until this horizon, but also the development of renewable onshore or offshore or photovoltaic energy. And maybe we shall consider later some import of hydrogen in order to access to this balance between to achieve this balance between supply and usages. Next. The second priority for us, second challenge, is to scale up. As I said previously, the main obstacle is still the cost of the technologies. These technologies are mature, of course, but still too expensive. So we have to contribute to the, I would say, the blooming of large-scale territorial ecosystem. So to massify, to gather usages on all sectors, industry, mobility, energy, in order to be able to build large-scale electrolyzers and to produce hydrogen at a lower cost. There is also a need to develop the industrial offer. As I said, gigafactories of electrolyzers still to be need to be built. The same for fuel cells. As far as vehicles are concerned, there are very few trucks, no waste trucks. So very few cars, very few vans. So we have to develop this industrial offer. And what is also very important, and which was not so much stressed before, is to make the link between the supply and demand. So everything concerning logistics of hydrogen. So it's about transport of hydrogen, either gaseous form or liquid form, and also the distribution infrastructure, all this hydrogen refueling station infrastructure, which has to be installed in order to give some comfort to the users. And we have also to develop usages within the downstream sectors. So in a nutshell, we have to build a new market, and it's a tremendous work to do. Next. So which deployment we consider? We consider that the best areas where hydrogen can develop are harbors, are valleys, some valley, and also, not yet, and also the borders, where there are already some some common project with neighboring countries, with Spain in the south, with Germany and Luxembourg in the north. So the harbors of Dunkerque, Le Havre, Nantes, Bordeaux, and Marseille. And within this, what we call a basin, there would be a pooling of some large ecosystem. So within this basin, we can find industrial platforms, harbors, activity, maybe airports, and also logistic platforms. So in this basin are very good in order to massify and to find condition in order to develop properly hydrogen. Of course, so we have also to combine all this to combine this approach with logistic means. So to consider even now some links between this basin and also to link this basin with logistic corridors which are already on the table at the European level. Next. And more broadly speaking, there was last week a study which was published by 23 TSO, transmission system operators, in order to develop a huge hydrogen network at the level of Europe, retrofitting partly what exists in terms of natural gas networks, 70% roughly, and building new pipes in order to establish, to create this connection between production centers and utilization and users. Next. I will just show rapidly what is at stake concerning buses and trucks. We have today a plan for developing 1,000 buses in France by 2024. So far, we are also halfway. Some buses are already circulating in France. Some are ordered, and a lot of cities, roughly 20 cities, have expressed an interest to buy buses. Next, the same for the trucks, and especially with, I would say, refrigerated trucks to convey fruits and vegetables to the users. Next. Next. And the third challenges we have in front of us is to contribute to the reindustrialization. And for that, we will try to maximize the local content of the project and to reinforce all the components of the value chain. And also, we have to develop competencies and training in order to prepare the workforce for this new activities. What we have seen with the COVID, with this pandemic, is also that sovereignty, economic sovereignty and technological sovereignty is very important, and in this area as well, it is very, very important. Next. So as a conclusion, hydrogen will not do everything, but without hydrogen, we will not succeed within the ecological transition. Hydrogen is a versatile energy carrier, so in every case, we have to adopt a holistic and systemic approach. As I said, the costs are still too high, so we have to massify, to scale up, to build this territorial ecosystem in order to achieve this large-scale project. Of course, we have also to maintain a high level of research and development, and we have to foster innovation. This will be done within a European context framework. And last but not least, I would like to say that at the end of the day, we have to work on both legs. Means we need regulation, a good regulation, which give visibility to the investors, but also some financial support. And in that respect, a carbon tax would be very helpful in order to foster these projects. Thank you for your attention, and I will be prepared later in this morning to answer to questions.
Thank you, Mr. Boucli, for this very extensive presentation. I was particularly interested, but we'll probably have that in the question, by the articulation between the state effort and budget and the billions that will be put by the government, but also the strong wish to have an industrial part in that, and as you say, the reindustrialization, and also the articulation between what will be done in Europe, but also in France at the national level, but also at the local level. And I think this is very important, as you say, in the territories, like we say in French now. So I think this duality is very interesting. So we'll probably have that in the questions later. So this was the first part about the global overview, both in France and the UK. And now we are going to a second part of our webinar. So with a little bit more R&D approach. So this makes sense because I forgot to mention it in the beginning, but this seminar was organized at the French Embassy, mostly by the Higher Education and Research and Innovation Department, so dedicated to R&D, and with the support of the Economic and Nuclear section. So we did first, if I may say, the economy and policy. Now we will delve a little bit deeper on the R&D part. So first, I will ask Mr. Paul Jordan to give his presentation. So Paul has more than 24 years experience in the energy sector. He's now working to support the energy systems Catapult. So he knows this Catapult system very much, since he's working for the Catapult Accelerator, Energy Launchpad, and the international team. So he will give us a more, I would say, technically or R&D oriented about the challenges linked to these hydrogen plants. So, Mr. Jordan, you have the floor.
Thank you very much, and I will certainly try my best. And bonjour, everybody. So just start with just a very quick overview of the catapults, the energy systems catapult. So Jim talked a lot about the systems approach and has historically been a non-exec director at one of the sister catapults, the offshore renewables energy catapult. There are actually 9 catapults overall, covering various sectors, and but essentially what the catapults do are really, I like to think about it as 2 aspects. One is trying to help address the challenges within the growth of particular sectors and understanding those barriers and helping to overcome them. And the reason for that is ultimately we want to help accelerate the scale up of new innovation and new solutions into those sectors. So we do that through what we call a whole systems approach. Catapults were set up by government to progress this, but we are all separate, independent, not-for-profit organizations, and that allows us really to be an essential convener of many of these aspects that are needed to address these big issues like hydrogen. So what do I mean by whole systems thinking? So Jim has already gone into this in great detail, but just highlight here that this is some of the way we try to explain this, and it's key to really think about the fact that this is not just about individual energy vectors, so electricity, heat, transport, etc. It's also about the wider aspects with respect to the legacy infrastructure that we might have, but it's also about the end user and the way in which societal changes are affecting the energy transition. So a lot of what we do thinks about the end user and the consumer and the value and the service propositions and business models that need to change here. But then also lastly is how does the market change? How does it evolve? How does the policy and regulation play into this? And we just heard in the last presentation, in that conclusion, that this is very much with respect to hydrogen about creating that market. So that's really the context here, and hopefully this builds on what you've heard so far. So hydrogen, we did some modeling of the national pathways out to 2050, which we launched this time last year. It's our Innovating to Net Zero report. Again, it's all publicly available. Please do follow the links here. And we modeled the UK in that change from 80% decarbonisation to 1990 levels to net zero by 2050. And the big change from going from 80% to net zero, really, the biggest change really was that hydrogen has a much bigger role to play in net zero. Our modelling showed that use between 200 to 300 terawatt hours per year. There's different ways to look at that, but that is huge. I've put a little back of the envelope calculation there to show that that's between 13 to 20 million UK homes of total energy consumption. So that's including heating. Another way to look at it is that this is the 200 to 300 terawatt hours per year is approximately the same as the total electricity consumption in the UK. So these are big numbers. Breaking that down, then you can see that there's other vectors that are key here as well, and this goes back to that point around the whole system approach. So the hydrogen aspects really feed into the changes that you're seeing with respect to electrification and also district heating. And one of the key things here is that local area energy planning and developing the best solutions for net zero across all of these vectors at a regional level is really crucial to help select which way do you go with respect to electrification, hydrogen, district heating, etc. There are also many recent UK government announcements that could potentially open up the opportunities for hydrogen. We've already heard about some of these, but many of them relate. So even the fact that there's a high target there for offshore wind, that relates to hydrogen with respect to if there's excess electricity from renewable energy, how does that play in? Changes with respect to banning of internal combustion engines for vehicles from 2030, moving to 100% zero emission vehicles by 2035. Is that battery? Is that hydrogen? The buildings in terms of the ban on gas boilers, hydrogen production. There's talks about hydrogen towns being 100% hydrogen, trialing those from 2030. Pushes on nuclear, which obviously is going to be a particular relevance to France. That opens up opportunities with respect to links to hydrogen and carbon capture and storage, which is critical on many of the hydrogen options. So getting into a bit more detail here. So, I mean, one of the things that I quite like about hydrogen is the range of colours that are spoken about here. You know, we have grey hydrogen, blue hydrogen, green hydrogen, purple hydrogen, turquoise hydrogen. I'm sure there'll be many more colours that come through as we delve into the growth of this sector. But the point I'm trying to make here is that there are many, many different ways in which hydrogen can play out here. I've just illustrated two here from National Grid's energy scenarios. So at one end, you've got blue hydrogen, steam methane reformation with carbon capture and storage. That's one way that allows us to utilize some of the existing gas grid. But you could go to something that's much more renewables based in terms of electrolysis and green hydrogen and the repurposing of that excess electricity. Those other colours that I mentioned, you know, in terms of purple hydrogen, in terms of using nuclear. There's also turquoise hydrogen with respect to pyrolysis. So there are many, many different options here for how this can play out. And that's just to highlight that this is a real challenge here. And again, links to what Sir Jim was talking about there with respect to the fact that the systems engineering approach is absolutely critical to addressing this. So just talking about a couple of those sort of changes here, again, going back to our Innovating to Net Zero analysis. So this is looking at hydrogen production, and you can see here that between two scenarios, so our clockwork scenario is a much more centrally driven, centrally directed kind of approach, and patchwork is a much more decentralized scenario. And you can see a couple of interesting aspects here. So one is whether or not you are going down the route of using existing fossil fuels with carbon capture and storage to generate that hydrogen, or whether you go to electrolysis, as I just mentioned earlier. Another key aspect is biomass with CCS. So you can see how important that is, particularly in the patchwork scenario, and that's also highly important because biomass with carbon capture and storage for hydrogen does allow for negative emissions to be introduced here as well. So that again does have an important role to play in production, and you can see then between the two scenarios how heavily that plays in, and also the timing of that. In terms of consumption, again, one of the big changes here between that sort of centralized approach and decentralized is really that aspect of heating. So in the UK, that's a critical area that we need to address for net zero. And you can see there's really a choice there between whether you go down the route of hydrogen boilers, repurposing the existing gas network, or potentially hybrid heat pumps, where you might have a boiler coupled with a heat pump and you use the hydrogen for the peaking applications, and also reduce the demand on the need to upgrade the electricity network, or whether you go straight to electrification and therefore the demand for hydrogen for heating is much lower. One thing you do see between the two scenarios, and this goes back to some of the least regrets, and I think you've seen that reflected in the last presentation, is areas like industrial decarbonisation. You really see the same scenario play out there with respect to industry, and that's because many industrial processes, whether cement or glass or some of the steel, etc., some of those industries, really there aren't many alternatives for decarbonisation other than hydrogen, and so you do see that play out in many of the scenarios, irrespective of the route forward. And then you do see, as again, shipping is another area that is important here, and then transport as well. And transport, well, depends on whether you're looking at heavy duty vehicles or perhaps potentially even rail and aviation. So this is really the key slide here. So what does this all mean? And what I've tried to do here is capture really the challenges, and I do kind of highlight here that really there are still many unanswered questions with respect to hydrogen and how this will play out. But we do have a much deeper understanding of those issues that we need to tackle and what those potential solutions might be. So if we just cover off, blue hydrogen, for example, that's got some great advantages in terms of volume production. We already have the networks already there, but it does need carbon capture and storage in terms of being contributing to net zero, and we do need high capture rates there. So a lot of R&D still needs to go into CCS and increasing capture rates. Green hydrogen, yes, great. We can move straight to something low carbon, but electrolyzers are expensive. They also need to be produced at scale. Going back to my first slide around the volume of hydrogen that we're talking about here, that's a lot of electrolyzers, and a lot of R&D needs to go into bringing the cost down of that. There's also a question mark about the advanced nuclear role. How will nuclear play into this, and also pyrolysis, which was mentioned as well. Storage is critical. In the UK, we do see a potential for UK salt caverns. There are already over 30 of those used for storage of methane already. So it's not beyond the realms of possibilities to start to ramp up the capability there for storage in those salt caverns. And that could allow us to store large quantities and allow for one of the big benefits of hydrogen in terms of seasonal storage, which again is one of the big issues with respect to heating. Depending on the way that goes, you see the heating demand ramp up massively in the winter months, and therefore having some form of seasonal storage would be very beneficial. Distribution, this really is dependent on volumes and end use. I mentioned 3 alternatives there earlier. Is it using the existing gas network going into hydrogen boilers? Is it some form of hybrid system with hybrid heat pumps using hydrogen for the boiler and the heat pump on the electricity grid? Is it moving directly to a pure electrification for heating, in which case hydrogen might just be more of niche applications around industry and maybe some of the transport applications. Others are also considering ammonia as a vector to transport hydrogen. It's much more energy dense, and a lot of research going into this area, which could be interesting. And there's already an industry around ammonia, so it's not again, it's sort of building on something that already exists. Industry we sort of talked about. It's pretty much the lowest regret application here, but there is a need for clustering because if we're going to do that and we're going to need to do the carbon capture and storage, there is a need to think about industrial clusters and how we bring those together. Also, the big advantage of industrial decarbonisation is that could be a way of de-risking the hydrogen networks for other areas. So, for instance, you could start to see a rollout of hydrogen into local transport systems. Maybe you could use that for local, so for heating solutions domestically and for commercial industrial buildings locally to those industrial applications. Transport has a very high potential, but there are strong competitions for other solutions, particularly in passenger cars. So battery solutions, we see lithium-ion batteries dropping in cost significantly. So does it make sense for hydrogen into, say, passenger cars? However, there are many vehicles where this would make sense, heavy-duty vehicles, vans and passenger cars that are going on long distances or traveling a lot. So taxis, for example, also buses we've spoken about there as well. So there is high potential there, but it may be on a case-by-case basis that we need to pick the appropriate solutions. And I did as well talk about there is consideration for rail, particularly in rural applications where the electrification of the rail system may be more difficult. Again, could be a good route for hydrogen. Heating, I think I've spoken a lot about there, uncertain as to which way that goes. And also, even if we do go down the hydrogen route, there's a lot of work still needs to be done to understand the health and safety aspects, the economics, making sure that there's strong consumer buy-in. And lastly, power generation is another interesting area. So there is some value here on peaking plants, but there is going to be need for some further R&D, particularly into hydrogen turbines. But again, it's not a massive leap to see gas turbines move towards being hydrogen turbines. This is my last slide, and this is just really to highlight in the UK, there is a huge amount of activity. Again, you heard earlier from Sir Jim, a lot of great work going on in Scotland with particularly around Orkney and what have you. But this really is just to try and show that it's a very, very complex picture, and there is a need to look at how the appropriate solutions can be adopted for the appropriate applications. We're heavily involved in a project looking in Milford Haven in South Wales, for instance, which is really starting to think about the architecture for how many of these aspects come together. We're working closely with the offshore renewables Catapult there because of the links with offshore renewables potentially and future liquefied natural gas growth application there as well. But thinking about how the architecture could come together and how that might be a model that could be used elsewhere for the linkage of both the generation and the supply side as well as the consumption. And lastly, I just reiterate what we see as a really key point here, which goes across all of the net zero applications, so not just hydrogen, is that local area energy planning really is critical for allowing for the impartial decision making around some of these applications at a regional level, and having that sort of model rolled out, we think is essential. So hopefully that just gives a little bit of a flavour of some of the challenges there and some of the R&D activities that are underway, and very much look forward to the questions and answers after the final presentation. So thank you very much.
Thank you, Paul. Thank you for your presentation. It was very interesting to see that behind the big plans, the big numbers and so on, you have so many options, so many practical decisions, like you know, the simple thing like heating a house with hydrogen boiler or with electricity, and the networks also option. So this was really a detailed insight of all the potentials, but also all the difficulty to make the good choice. So I'm sure we'll have some question about that. And I will seize the opportunity also to thank Catapult Energy System to help us for this webinar. You are our partner in the organization, so thank you very much for that. Now I turn to my last panelist from the UK or French side. Of course, we'll have some European perspective after. So Hélène Burlet from CEA is with us today. So Hélène has a long career inside CEA. So CEA, everybody knows CEA for its nuclear activities, but CEA, and she will tell us about that, does also alternative energies, and especially CEA works on hydrogen. So CEA joined the the laboratory for new energy technology, and after she became deputy head of this laboratory. And now she's deputy director at the Directorate of Program for the Direction of the Energy. So the Direction of the Energies as in CEA the hand for all the programs concerning all the energies, be it nuclear, but solar, hydrogen, and battery, and so on. So Hélène, the floor is yours for your presentation. Merci beaucoup, Hélène.
So thank you very much. So good morning, ladies and gentlemen. So our previous speakers have largely mentioned the role of hydrogen in the energy transition and climate challenges. But in fact, a large deployment of energy of hydrogen technologies still requires significant research and development efforts to make such technologies accessible to all, especially due to their high costs, too low performances, and the lack of standards and regulations today. So, of course, I will just comment the key challenges to address is to reduce costs and improve performance. But before, I would like to give you a brief picture of CEA activities on low carbon energy. So here you have on this slide, you can see that our activities at CEA is split into 4 main axes. The first one is production, second one is systems, third one is resources, and finally energy mix. So considering production, CEA is developing low carbon energy, so especially through nuclear reactors and also through renewable energy. And we will speak especially on production of photovoltaics. But this is production. But in fact, our main activities is probably on this great axis, which we call system. It means that today we cannot develop a production, we cannot develop fuel cells, usage, and things like that without looking all together and looking to all the interdependencies between all these components. And in fact, you have a big problem, which is the smart energy grids, which is the link between all the production and all the consumption and the consumers. So we developed smart grids activities, smart energy grids, and not only electricity. It means that we work on the 3 vectors, which are electricity, but also gas and heat. And we look on how to manage these three vectors, these three grids, and to make them work all together for a global optimization of the energy systems. So of course we work on flexibility systems, we work on batteries, on storage, on hydrogen vector, conversion, so to improve efficiency. And thirdly, this is so big activities at CA, and thirdly, we work also on what we call resources. It means that today we cannot develop any new technology without taking into account the problem of resources, the problem of critical materials, or access to some material. And of course, we think of circular economy, so all development are performed under circular economic constraints. And finally, we also look on scenarios, we look on technical economic models. It means that today, if we develop a new technology, we must be sure that it will be possible to deploy it largely. It means that it is economically viable. And we also have to look on life cycle analysis, global life cycle analysis, and also on social acceptance. For all these subjects at CA, we are some around 2,200 employers. Some key figures here, so 250 patents deposit per year and a global budget of 400 million per year. So we have also a focus here on hydrogen activities, as you mean hydrogen, and you can see hydrogen is one of our activities. So these activities are performed through some 120 employers. And at CA, we work on production, storage and transportation, conversion, and cross-cutting activities. So just one focus on production. We have our activities on production of hydrogen through electrolysis and high temperature electrolysis more precisely. Have given rise to one startup called Silfen, which work on a smart energy hub for buildings and for district, and a more recent joint venture society called Genvia, which mission is to develop clean hydrogen production on solid oxide technology. So with an objective of gigafactories in 2027, as already mentioned, in fact, by Philippe Bouclé. This is one of a project of gigafactories with the help of French funds. So now if I come back to research activity and research needs to deploy all these hydrogen technologies. So in fact, I will speak now on the, which is also already mentioned by Philippe Bouclé, which is called the Priority Research Program in France. So which will work on production, storage and transportation, conversion, and also uses. So this program, the main objective of this R&D program is really to lower costs. So it has already been mentioned that mass manufacturing is, of course, one solution, one way to decrease cost, but you can also think to other solutions to decrease the cost. For instance, by using less critical and expensive materials, so by replacement of platinum, for instance, in some fuel cells. You can also think of new processes that are lower expensive. You can, of course, think of improved performances. So, for instance, we have to improve current density, for instance, for some membrane of electrolyzers. You can improve also, this is very, very important, is also to improve lifetime. So to work on stability, to improve, to work on stability, to better, for instance, to better understand how mechanism of degradation happens. So if you understand the mechanism, You can propose solutions, for instance, with other materials, or for instance, to develop coatings, or you can also think of better management impact of the components. So it means to develop advanced energy management systems. If you want, what could be very important, very useful, is to be able to remain the components in its better range of operating. It means the good, for instance, current, or the good voltage, or the good temperature, to be sure that it remains in these optimum conditions, to be sure that you can increase the lifetime and you avoid any degradation mechanisms. So you can see that we have many, in fact, R&D to perform, to increase lifetime, to understand the mechanism, increase lifetime, develop management systems. And also in this program, the hydrogen is also seen as a key factor to develop advanced fuel. So, for instance, you can use hydrogen to develop what we call e-fuels, with combination of CO2, and to develop either liquids or gaseous electrocurrent or electrofuels. So this is also considered in this big research program in France. So on the right side, you can see that you have also another activities which are very, very also important, and we must take into account, which are around the life cycle analysis. It means that we really must understand all the footprint, the environmental footprint of one component, of one technology, from its manufacturing, its usage, and also its recycling, or how it is and its end of life. So we will develop methodologies to measure life cycle analysis. This is very important because the methodologies are really needed. We will have also activities on safety programs and standards, which is very important to develop standards at, in fact, international levels. And we also have activities on social acceptance, which is very also important. My last slide here describe, in fact, more precisely the kind of activities which will be found within this priority program, French program of research on hydrogen. So you can see, for instance, on production of hydrogen, we will improve, in fact, the already existing technology, which are already mature. Even some of them are even commercially available, such as, of course, the alkaline electrolyzers, or you have also the proton exchange membrane electrolyzers, and which is already commercial available, but we have still R&D research to perform, to conduct, to decrease the cost, as I already said, to develop new catalysts. For instance, for the PEM electrolyzer, we need catalysts, new catalysts with probably less platinum, or even without platinum at all. And also, for instance, we have to develop a platinum group metal-free electrodes. Concerning a high temperature electrolyzer, we need to improve current density, and especially much work have to be performed to improve lifetime. So that means to understand really how degradation mechanism are underway. But this is not all the activities on production. We also want to found and to develop alternative technology which are less mature, but which are very promising. For instance, we will work on development of alkaline membrane for electrolyzer, so which improve conductivity and durability. Work will also be performed on protonic solid oxide cells at lower temperature. It means around 600 degrees Celsius. We will work on solar hydrogen by coupling photovoltaics and electrolyzer, or more innovative direct photocatalysis. And we also develop activities on biological hydrogen, and with much work on catalysts. And we will also perform some activities on how to couple electrolyzers through renewable sources. So this is, as you can see, much activities. And there are also many activities on storage and transportation with liquid hydrogen under cryogenic conditions, and work we will perform on thermal insulation, boil-off losses. We will also look on liquid massive storage through liquid organic hydrogen carrier or ammonia. We also work on gaseous distribution of gaseous hydrogen through pipelines and the problem of hydrogen embrittlement. We will also make activities on solid-state materials, complex hydrates, we have the objective to increase weight density. We will also develop innovative pressurized tanks for heavy-duty vehicles. And we will also have a look on geological storage, salt caverns, aquifers, and so on. So as you can see, very different solutions to, in fact, address different usage. And fuel cells will also give rise to activities. For PEM fuel cells, we need higher power, we need lower costs, durability, higher durability, especially for heavy-duty transport. And concerning solid oxide fuel cells, we work on flexibility with other fuels, not only hydrogen, but it's very important. These fuel cells can operate with, for instance, ammonia. We can work also with methane and so on. So this is very interesting, and innovations and work will be conducted on this flexible fuels for solid oxide fuel cells. And we will also perform activities on energy management system with new power electronics. And we have also activities, we will have also activity on hydrogen combustion thermal engine, for instance, for airplanes. And as I already said, we will perform work on life cycle analysis, recycling, eco-design, economic and social analysis, safety problems, standards, and so on. So all these activities, of course, we rely on theory, modeling, simulation, which are cross-marketing activities, and advanced characterization. Just for an indication, for all this program in France, the government allocated 65 million euros. Well, thank you very much for your attention.
Thank you, Hélène, for your slides and your presentation. Very interesting, particularly what you mentioned many times about the life cycle analysis, which means that you have to really look at all the aspects of a certain type of energy from cradle to grave, if I can say. And many thanks also for developing all the numerous R&D area that are necessary in order to make this energy transition using hydrogen a reality. I would now invite our last speaker from the European Commission to give us a European perspective. We are running a little bit late, so I'm sorry because he's the last. I will ask him to be compact in his presentation. Pierre Michel is a seconded national expert for fuel cell and hydrogen joint undertaking at the Commission. He has an extensive career both in France at international level, since he worked in the States and in Poland, especially worked in the embassy to foster the cooperation between France and these countries. And now he's at the EU, and he will tell us about the EU perspective on the, hydrogen. We know that EU is putting a lot of effort, and we will be hearing from him now. Pierre Michel, the floor is yours. Thank you very much in advance.
Thank you, Pierre. Do you see my screen?
Yes, we do.
Okay. Well, I will say a few words about the fuel cell and hydrogen joint undertaking, which is a public-private partnership supporting research development, technological development and demonstration activities in the fuel cell and hydrogen energy in Europe. So it was established in 2008 by European Council regulation, and it was renewed under Horizon 2020 in 2014. So I will use the acronym, sorry, FCHJU, because it's a long word to spell, Fuel Cell and Hydrogen Joint Undertaking, in my presentation. So the aim of FCHJU is to accelerate the market introduction of these technologies, and the R&D activities, the R&D activities are split in three main pillars. The first pillar is energy, which is, as you know, the first contributor to CO2 emission. And the second pillar is transport. And the last one is cross-cutting, and it's dealing with safety, regulation, code, standards. It was already addressed by the previous speakers. Regulation, code, and standards are very important to allow the deployment of this technology. So up to now, in late last year, we had 285 projects supported for a budget of approximately 1 billion euros. And the same amount was leveraged from other sources like, of course, industry and other partners, national member states. So as you see, that's split in approximately 50% in energy, well, 45% in energy, 41% in transport, and the rest is on cross-cutting and overarching activities. So I will be quick because we are running late, but it was already addressed by the speakers, my previous speakers. Hydrogen today is produced with steam methane reforming. 99% of hydrogen today used mainly in industry is produced with methane. Well, the aim of FCHGU is, of course, to support green hydrogen. Hydrogen can be used to store renewable energies. It was mentioned in above ground or large underground storage for seasonal storage. Depending on the demand of electricity on the grid, it can be converted back to electricity with fuel cells, and that's what we call grid balanced services. Green hydrogen reduces our dependence to fossil fuels. It's an integration vector in all sectors of economy. It's a feedstock for industry in the so-called hard to decarbonize sectors, especially refining industry, which is the main users today of hydrogen, the production of ammonia, fertilizer. Unlike batteries, green hydrogen can be used to electrify the transport sectors with fuel cell electric vehicles, which, as you know, are zero emission vehicles. The only emission is water. Hydrogen will also contribute to decarbonize the aviation sector, and I will come back later on that, with electric propulsion or synthetic fuels. In heating, and I think in Scotland is really in advance for that. It's used for in buildings in the so-called micro combined heat and power units. As you may know, there are already 300,000 micro CHP combined heat and production unit in Japan. And it's also coming, of course, in Europe, and we're supporting this sector. Of course, the price, and it has been mentioned earlier, is still a barrier, but the scaling up of the production will make this technology more competitive. So in transport, I will go quickly, but all sectors of transport are concerned. The most promising decarbonization option are for aviation, ships, trains, trucks, buses, well, all sectors. And if you compare to batteries, of course, batteries are much more deployed right now, but they have a lower energy density, then a lower range, driving range. They have they are heavier, the weight is a problem. They have a slow recharging performance in comparison with hydrogen-powered fuel cells. Well, there are several car manufacturers already in the world, not many in Europe, unfortunately. Toyota, of course, is the most advanced, so with the Toyota Mirai, Mercedes, Honda, Kia, Renault, and soon PSA in France, with a consortium with Symbio and Michelin and so on. But a very common application now on the market are the fuel cell forklifts used in warehouse. For example, Walmart and what we call material handling vehicles. Walmart and Amazon uses thousands of them in the warehouse already. I will come back later on maritime and aviation and trains. So to come back to our activity and a small summary of what FCHDU has supported since the last 10 years, I would say. Regarding cars, FCHDU has funded 1,860 light vehicles. And right now there are almost 1,000 vehicles deployed in Europe on the European roads. The application, most of them are in captive fleets because the problem is still the infrastructure. There are not so many refueling stations. So when it's a company or a fleet of, let's say, commercial vehicles, it's easy to have one station and the vehicles are coming back every day to refuel. And the refueling is only a few minutes. As you know, hydrogen is stored in onboard tanks at a pressure of 700 bars. And the typical tank is about 5 kilos of hydrogen. And the hydrogen consumption is around 1 kilo of hydrogen per 100 kilometers. So the driving range of these vehicles are equivalent to the, let's say, the diesel engine or any thermic engine cars, combustion engine cars, and it's about 600 kilometers. And the main advantage compared to batteries, of course, is the refueling, which takes only 5 minutes. So as I mentioned earlier, the Japanese and Korean manufacturers are dominating the market. But I mean, the European OEM and manufacturers are coming on that market. So regarding buses, it's also a promising application. Fuel cell buses and coaches for long-range coaches. As you know, these fuel cell coaches and transports as a whole account for 27% of road transport emissions. So it's a great challenge. We have, FCHDU has funding a study which shows that fuel cell trucks and coaches can compete with battery electric vehicles. So I will give a few figures later on. Actually, for long-range application for transport, there is no other solution, but you cannot think of batteries for a range of more than, let's say, 500 or 1,000 kilometers. Because these applications require large autonomy and fast refueling solution, which cannot be provided with batteries. A survey among passengers for the buses has shown that a great acceptance, the fact that the buses are very quiet, provide a smooth, comfortable ride, and without, of course, any pollution in the atmosphere, which is also very important in cities. So the European cell manufacturers are Daimler, Van Hool, Safra in France, VDL in the Netherlands, Solaris in Spain, Rampini. So almost every, Western Europe has a manufacturer of this type of buses. And regarding trucks, which is another important challenge for decarbonizing transport. As you know, Europe, the EU legislation is pushing for stricter emission and pollution standards in transport to achieve a 90% reduction of emission by 2050. And heavy-duty trucks are a very large contributor to this emission, about 5%. And it's absolutely necessary to switch to zero-emission vehicles. And right now, the main obstacle is the cost of hydrogen, it was mentioned, and of course, the cost of these trucks. A study funded last year by FCHDU and carried out by Roland Berger Consulting Company has shown that fuel cell heavy-duty trucks can become cost competitive with conventional diesel as soon as 2027, so in a few years. Of course, this will require a scaling up of the production and the price of hydrogen below 6 euros per kilo at the pump, which is feasible. The study project a potential fuel cell trucks sale approximately a share of approximately 17%, sold in 2030 in this scenario. So it would mean about 60,000 fuel cell trucks in 2030. Well, in 2027, these trucks will provide operational performances comparable to diesel trucks regarding daily range, refueling time, and payload capacity, and even at a better total cost of ownership than the incumbent technologies. Another application is trains. We have supported with another partnership called Shift Rail, which is also a joint undertaking. Of course, it was already mentioned. There are some regions where there are no electrification of the lines. So, and it's very costly to install catenaries. So fuel cells can provide an alternative solution for these non-electrified lines. Over 100 kilometers in length, they could become competitive. So there are already hydrogen fuel cell trains in service in Germany, in the Netherlands, and SNCF, the French National Railway Company, has last week announced an order with Alstom in 4 regions for 12 hybrid hydrogen electric trains. So these trains have a range up to 600 kilometers on non-electrified track section. Toyota Motor also has announced that they will supply and integrate fuel cell modules in zero-emission trains with a project supported by FCHEU. It's a consortium made of partners from Belgium, Germany, Spain, and Portugal. And aeronautic application, it's we had many news lately in the news, and especially in the UK, but not only. A recent study commissioned by Clean Sky, which is another GU, and FCHEU on hydrogen potential for use in aviation, found that hydrogen as a primary energy source for propulsion, either for fuel cell or direct burn in gas turbine engine, or as a building block for synthetic liquid fuels, could feasibly power aircraft with entry into service by 2035 for short-range aircraft. And the additional cost would be less than 18 euros extra per person on a short-range flight. And it will, of course, have a huge impact on climate, reducing the climate impact of aviation by between 50 and 90%. As an example, an Airbus 320 contains 23 tons of kerosene, and 9 tons of hydrogen would be sufficient to have the same amount of energy. So, of course, there are many challenges to solve. If we think about electric engines powered by fuel cells, then we will have to store liquid hydrogen on board these planes at a temperature of minus 253 degrees. Of course, we cannot envisage compressed hydrogen. It will require heavy tanks, and it's not acceptable in planes. So this will, of course, necessitate the development and the deployment of hydrogen production in the vicinity of airports. So the use of synthetic kerosene made with green hydrogen is another solution, and probably it will be more feasible in the first phase. And as you know, Airbus has revealed 3 concepts for the world's first zero-emission commercial aircraft, which could enter into service by 2035. And I know that there are many also experiments in UK with a UK company for transforming a conventional aircraft with a fuel cell powered and electrical engine. And about industry, it was mentioned so far today the industry is the main user of hydrogen. And we have, and the challenge is, of course, is the scaling up of the production. We must be, if we want to reach the objective, the European objective of 40 gigawatts in 2030, we have to build, of course, larger and more powerful electrolyzers. So this picture gives an overview of what's happened in the last 10 years. We have supported 68 projects related to electrolyzers, and with a budget about 200, and storage and distribution included is 200 million euros, and 2/3 of the budget was for electrolyzers. In the last 5 years, we provided more support to solid oxide electrolyzer, high temperature electrolyzers, which can work in reversible modes, and that is to say in fuel cell modes to produce electricity and heat. And so it's very useful in many applications. So the graph showed a fast evolution on scale. The capacity of electrolyzers was a few hundred of kilowatts in 2011. And now we are in the range 10 to 20 megawatts with a large industrial project. And the target of the EU is to reach 100 megawatts in 2025 and the gigawatt scale in 2030. And this is in line, of course, with the objective of the 40 megawatt gigawatts installed in 2030. An example of an industrial project, and I have only 2 or 3 slides more. This is an application in industry. In Germany, it's the project Refine. I mentioned it in my previous slide. It's a very large electrolyzers. And of course, if you think of this, the size of this factory, you have to imagine that to install 100 megawatts of electrolyzer, you need approximately the surface of a football playing field. So today, this is the largest refinery, shell refinery in Germany, and it requires approximately 180,000 tons of hydrogen, which is produced with fossil fuel, with natural gas. And the refined 10 megawatt electrolyzer project is the world's largest PEM electrolyzers being implemented currently in this refinery. And it will start in 2021. And now maybe an initiative of the European Commission and the FCFU has launched several schemes and programs to raise awareness and help cities and regions in Europe and member states to advance the commercialization of FCH technology. So we have launched what we call a project development assistance to help develop detailed project planning in regions and cities, and with a lower maturity level, and with a special attention to Central and Eastern Europe. So the FCHU has facilitated and supported a group of leading regions to set up the so-called European Hydrogen Valleys partnerships, and 24 participating regions and cities have expressed an ambition to become a hydrogen valley. In these regions, all applications are present, transport, energy, industry. So that's what we call an integrated sector for hydrogen. So I don't want to, we are late, so I don't want to give too much detail on this. Everything is our website. Maybe my last slide is about the market, and of course we have to create that market. It was already mentioned. FCHU was started in Horizon 2020, and as you know, it has come to an end, and now we are entering the new phase of Horizon Europe. So under Horizon Europe, a new partnership will be set up to continue our activity. And this slide shows a study made by Hydrogen Europe, and with some interesting figures. In 2050, hydrogen could represent 24% of the final energy demand. It would make an abatement of CO2 emission of 560 million tons. And the annual revenue generated by hydrogen and equipments would be about 820 billion. So this is a huge challenge for the European economy. Of course, there's also a huge impact on the health of citizens because, for example, the NOx emission in cities, which are responsible for many diseases, would be reduced by 15%. And it would probably create millions of jobs in all the supply chains if we are able to support the creation of this supply chain. So the main challenges, this has been mentioned earlier by Hélène, of course, is cost reduction through scaling up and automation, limitation of critical raw materials, catalyzer, like, for example, platinum, iridium, the reduction of electricity consumption of electrolyzers, of course, the improvement of the lifetime, and the development of large storage, underground storage in salt cavern or aquifers to be able to provide seasonal storage. And there's another challenge, which is the retrofit of natural gas pipelines for transporting hydrogen. And last but not least, standards and regulation and safety are very important issues, plus education and training, because we need to train new technician engineers able to address these new technologies. So FCHGU is not alone. We work on research and innovation to develop the building blocks, but the end users are co-developed with other joint undertaking. You may know 2.0 partnership, which is dealing with cars, clean aviation, zero emission waterborne partnership for the application on shipping. I was not too long on that, but there are also many applications in boats. It was mentioned with ammonia as a fuel for boats. P4 Planet is and the partnership for industry, and of course the Europe's rail system with the joint undertaking, the future joint undertaking transforming Europe rail system. Well, thank you for your attention.
Thank you, Mr. Michel. Very interesting, and especially the focus you put on transportation, whether by train, by car, by truck, by bus, and maybe by air in the future, was very interesting. I think it's a very practical application that the people will see coming very soon next to them. We have some time for some questions, so I will be very quick. We are today Earth Day, and this seminar is the first of a series of seminars that the embassy plans to do towards COP26. Professor MacDonald, how do you see the role of hydrogen towards COP26? Do you think that there will be a big emphasis put on the COP26 with hydrogen and its different aspects? Can you elaborate a little bit on that?
Sure. Well, I answered that question in the
sidebar.
That having been said, I mean, the COP26 is an opportunity to present the whole broad front of technologies as we move towards 2050. I think the notion of hydrogen has been around for many years. I think the truth, as we've heard from the presentations today, is this is now becoming a reality very quickly. And rather than as an opportunity, it's now being seen as a necessity. So it's clear to me, and the work of the Royal Academy of Engineering and the work that Paul is doing in the Energy Systems Catapult with his colleagues, is demonstrating hydrogen as part of an overarching energy system. And I go back to what I said earlier on. If we simply discuss hydrogen, I think we will not benefit from understanding its impact. I think if we see this in an overarching vision for a decarbonised energy production for energy, for transport, for industrial applications is key. So to answer your question, I am very confident that hydrogen will feature prominently at COP26. But most importantly, as we've seen from some of the questions in the sidebar, we have to move quickly now for large-scale projects such as Pierre just demonstrated in terms of the 100 megawatt scale, and then moving to gigawatt scale. And let's not leave it to the 2030s and the 2040s. Let's make sure we do this in the 2020s. That's what's very key here.
Thank you very much. Thank you very much. Another question we have, some of you mentioned about the cost of hydrogen. So how do you put that in your poll? Maybe with you. How do you put that in your simulation, in your projection, and how do you take that into account in the different options that are in front of us to select that or this technology? Cost would be an important factor, I would say.
Yeah, absolutely. We do factor in the different scenarios into the modelling. So we do look at whether or not different variations there mentioned around things like hybrid heat pumps in that patchwork model. The key issue with cost right now is that there's a lot of variability. I mean, the core, if you're looking at electrolyzers, for instance, using renewable energy, the feedstock is essentially the price of renewable energy. Now, the good thing is that's dropping. But then you've got to factor in, obviously, the capital cost of the electrolyzer, which can be anything from $250 a kilowatt extra capital cost on top. And also the other aspect of the costs here, it depends on the utilization of that electrolyzer, which is a really important factor that's often forgotten about. If you only have excess renewable energy a limited amount of time, your electrolyzer is only being used a very small percentage of its life, and therefore, of course, you're not getting the benefit from that extra capital cost. So the costs are vary a lot. I mean, just as a sort of rule of thumb, let's say, but as I say, it's a very broad range here, depending whether it's green hydrogen, blue hydrogen, grey hydrogen, etc. But if you're around, say, $5 a kilogram for hydrogen, you really need to halve that, really, for it to start to compete against other more conventional fuels. Ideally, $2 a kilogram for hydrogen is kind of a target that many people sort of talk about here, and some applications are at that point. As I say, if you've got low renewable energy, for instance, the electrolyzer has got high utilization, etc., then you can in some applications get to that. But if it's got to be on mass scale, then many of those aspects need to drop.
Okay, thank you very much. So I see that the race is on in order to have a more economical hydrogen, and there is still a big effort if you're talking basically that halving it or a little bit even more. Yeah. So it's very interesting. Thank you very much. About R&D, I will turn to Hélène. And so you showed basically what CA was doing in R&D for hydrogen. I guess many other R&D institutions in UK and France are doing similar work. Do you have already an indication or an idea about what would be the potential roadblocks? Because R&D, sometimes we can see where we are heading, and sometimes we can see that there is a bottleneck or a roadblock. Did you identify such a thing, and would it be in production, distribution, or something like that? Do you have an idea of the main challenges, if I can say, of R&D for hydrogen economy?
Well, I think that perhaps the main challenges is how to reduce the cost of hydrogen, of clean hydrogen, because if you don't have a competitive hydrogen, you will have really problems for the deployment of hydrogen. So I think the main efforts must be on this this problem, how to decrease the cost of low carbon hydrogen. So this is my opinion. Just a precision. The program I have presented is not CA program, is the program of and in fact I'm a co-pilot with CNRS of this big program. That's why I can give you many indications, but it's not only for clear, it's all French scientists and organisms who will work on this large program. Well, concerning your question, yes, for me, production without reasonable low cost of low carbon hydrogen, we really meet a problem. This is my opinion. Of course, fuel cells is a problem, because if you don't manage to decrease platinum, for instance, you will have costs which are really make the modification of the transport not affordable for everybody. So this is not just possible. So, well, everything is important, in fact, but perhaps production is the first bottleneck to address in terms of costs.
Okay, thank you, Hélène, and thank you for the precision about not being only CA program, but the whole French R&D program. Thank you very much. I see that Philippe Boucly joined us again. Thank you, Mr. Boucly. Right in time for a couple of questions for you. I have two short questions. First is you described the French plan on industrial case, which is very ambitious. Do you think there will be room for cooperation between British companies and French companies like consortium or joint venture in order to take part in this plant? in this plan? And second question would be, you insisted on the importance of the local development territories and so on. How do you interact? How do you exchange in France with the municipalities, department level, and so on? Do you propose, is there a master plan, or do you also listen to what these local authorities are saying, or is it more bottom up or top down or bottom up? What would you say about these two questions?
Again, sorry for being absent for some minutes, but I was in another embassy. Of course, there is a large room for cooperation between companies from both countries. Already now, the company ITM Power, which is producing PEM electrolyzers, is active in France and in Pau, for instance, where some hydrogen buses are running. The electrolyzer was installed by ITM Power, and I think with time there will be more and more such cooperation. What I notice as well is that in terms of buses, for instance, there are not so many buses producers in Europe, and two of them are from Great Britain. As far as local development is concerned, we realized, we as France Hydrogen realized that development of territorial ecosystem, large territorial ecosystem, was of utmost importance in order to scale up and to develop hydrogen in France. And of course, for that, we benefit from the strong commitment of regions. All the regions of France are members of France Hydrogen, and there are also big cities as members. And we have created what we call regional delegations, regional entities. They are not really entities, they are members of our association who are willing to contribute to develop this eco-territorial territorial ecosystems, and to build this project. Of course, our representatives within the region are not alone, and they will collaborate with the regions. In all the regions of France, there are agencies for the economic and climate, for economic and climate activities, I would say. And these agencies close to the head of the region are very active, and of course our people will collaborate with them. Really, the key for implementing our strategy is to foster this collaboration and to avoid to multiply all these small demonstrators. These demonstrators had were good in the previous period in order to install the idea of hydrogen within the mind of people. Now, I would say that this period is almost over, and now we have to gather to gather all these projects in order to create larger projects.
Okay. Thank you very much for your answers. One more question about Mr. Michel, you give us with this joint project about mobility, you studied the different ways to apply hydrogen. So you mentioned rail, aeronautics, buses, vehicles, small vehicles, large vehicles, and so on. In the near future, of course, we think that the most difficult will be plane, but in the near future, what would you see as the first concrete application, let's say in a couple of years? What could be the first that the French or European people or British people will see in their life, day-to-day life? Will it be the train, the bus, the small vehicle, the large vehicle, and so on? What is your opinion on that?
Well, the projections are, probably we will see more and more buses running on the roads. There are already many in Germany, in France, in all the countries, basically, and we have a few OEMs, European OEMs. I mentioned Daimler, Van Hool in Belgium, Safra in France, of course, VDL in the Netherlands, Solaris in Spain, right. Rampini, right in the UK, not to forget the UK. So we will see buses, and they are already on the road. And of course, we will support the deployment. And we have other means to support because we are more involved in R&D, but there are other European programs like the Connecting Europe facilities, and we are talking with them to enter in the deployment, in the large deployment phase, to finance hundreds and thousands of these buses all over Europe because there is still a price gap, but with the scaling up, the price gap will be decreased. So I think this will be the most visible by European citizens. But of course, if you look at the industry, there are already many applications. I mentioned the forklifts. There are thousands and thousands of forklifts working with hydrogen in industry, in the warehouses. We will see soon buses. Maybe in a few years' time, I think we will see, of course, not at the scale of the buses, but trucks. I would say heavy-duty trucks will be on the roads in less than 10 years. And of course, that will depend on many things about the carbon tax, about the agreement at the European levels. And to come back to the international cooperation, which is an important part, I think Mr. Boucli mentioned the important project of common European interest. There are billions of euros already committed by countries, and all countries will cooperate. I have in mind, for example, places where you can produce photovoltaic energy at very low price, like Portugal and Spain, produce hydrogen there, transport it by pipelines or by boat, liquefied, to Northern Europe. Rotterdam has a huge project to use hydrogen in all sectors, in maritime, in industry, in transport, in connection with Germany, Northern Germany. So this concept of hydrogen valleys are also demonstrating that it is possible to, and it is necessary to work on a transnational approach, because if we use hydrogen, we will need to develop infrastructures backbones in Europe, using existing pipelines, having common regulation. So this will be maybe the most difficult part, But to come back to your question, already we have already cars, of course, in very small numbers. If you look at Paris, you have something like 150 taxis in Paris, soon in London, but still for captive fleets. I don't see European individual cars, light-duty light cars for individuals, because there are still the question of infrastructure. First, we have to develop infrastructures, and the fund like Connecting Europe facility will help that.
If I may add some more words.
Yes, please.
Yes, as Mr. Michel told it just now, in Paris you have already more than 100 taxis with hydrogen, and the objective is to reach a number of 700 very soon, in order to demonstrate, to work on the full chain and to demonstrate to municipalities that it's a good solution to solve the issue of quality of air within the cities. Another area where the people could also experience hydrogen is the trains. As you know, trains are already running in Germany. Alstom developed such train, and very soon there will be also such train in France. And I heard that Alstom has also some orders from Italy or Netherlands. At least there was some test made in Netherlands, Austria, and Italy. So here as well, people could experience hydrogen very soon, on top of what Mr. Michel said about buses and so on.
Okay. Okay, thank you very much. I know that time is running out. I will have a last question, but maybe for all the panelists, you can have maybe a couple of words on it. You mentioned, I mean, Paul and also Professor McDonald, who has to leave, mentioned about de-risking. So de-risking the whole hydrogen project, de-risking the economy also. What do you think would be the most important in order to make this energy transition with hydrogen a success? What would be the most important thing to de-risk, to remove the risk? I don't know, Paul.
Yeah, sure. So I think it's very good to start with some of the least regret opportunities. We've heard of some of those already. So things like industrial decarbonisation, perhaps some of the transport options with things like heavy duty vehicles. We heard about some of the fleet applications with respect to things like taxis, etc., buses. That starts to enable clusters of activity there where you can start to test out some of these solutions. For example, if you need to link in carbon capture and storage, that's a lot easier to do when you have a cluster. And so you could cluster around some industry, start to move to hydrogen, develop the carbon capture and storage solutions, look at other storage opportunities for the hydrogen itself, things like that. That can also enable you to then link into local networks. So maybe you could start to link that hydrogen network for industrial decarbonisation into properties, whether that's domestic, maybe commercial, for heating. Maybe you can test that a little bit. You can start to test some of the standards and the health and safety challenges, ensure there's consumer engagement and buy-in to the change of technology there. And then you can start to expand that into other applications and allow you to scale more rapidly because you've proven that in those clusters. So that's a route that we could see making a lot of sense.
Thank you, Paul. Any other comments, Mr. Book? I think the most important thing we have in front of us a huge investment to do. It's about developing a gigawatt of renewables or nuclear power, gigawatt of electrolyzers, gigawatt of fuel cells, and so on. So there will be a very strong need of investment. And in order to foster this investment, to industry to realize this investment, industrial people need visibility. Keyword for me is visibility, and for that we need visibility for the support mechanism. So it's very important that this framework, this important project of common European interest, be in place very rapidly, in order to allow the respective government to help their champions. We need also regulation. There are a lot of texts at the European level which need to be adapted rapidly. There are again discussion, which is very good, about the renewable energy directive. There was a second version, then now there will be a third version about the corridors for energy or corridors for energy or for transport. This directive about alternative fuel infrastructure, and also for the directive about the gas. what it has take really for us, in front of us, it's a huge work to create a new market. Hydrogen was so far considered as a chemical product. Now it's an energy carrier, and it will be similarly to electricity or gas. It has to enter in a new perspective. And for that, we have to create an appropriate regulatory framework. And last but not least, in order to give visibility and to de-risk the investment, to have a carbon tax at the frontiers would be, I know it will not be very easy to implement, but I think we have to fight against carbon. We have to fight against CO2, and so the most direct means would be to have a tax against carbon. But I fully understand that it is not so easy within the present rules, which apply especially for the international trade, but it's really compulsory in order to go fast and to de-risk the investment.
Thank you, Philippe. Pierre and Hélène, any comment on the de-risking?
Well, I mean, Hélène, I don't know if you want to add something. On my side, I think Philippe Bouclier addressed all the main topics, and it has to be at the European level. And of course, with the close cooperation with member states, we need a common framework, regulating framework, and also having a view of the infrastructure in Europe and how to connect all the infrastructures. Another point maybe which shouldn't be should be taken into account is the education, because so far we don't have the trained people. It has to be taken into account at the university and the technical school level, because we will need, of course, a new workforce to work on these technologies, and the public awareness, because still hydrogen has a very strange image in the public. It's still considered as a dangerous gas, which it is like all gases. They are dangerous, but they can be addressed, and so this also is an issue, public acceptance.
Thank you. Interesting.
Yes, if I can just add a word, I think also safety is very important, because if you have an incident, one incident will be catastrophic for the hydrogen economy. So from the R&D point of view, it's very important to understand what are the real problems, the safety problem, and how hydrogen can escape and distribute, and what can we do to prevent all these risks on this point. On the R&D point of view, I think safety is a real challenge to address also.
Thank you. Thank you, Hélène. So we are, as in real life, I mean, as when we were doing real seminar before everything, we are a little bit late, but it's time to conclude. So I will thank all the panelists, and I will just conclude, if you allow me, by a 30-second remark, an historical point of view. It seemed from what I took from either Mr. Bouclier or Paul or Pierre and Jim McDonald presentation that in the future, the port city and the harbors might play a very important role for hydrogen. So it's interesting because harbors were very important for the humanity history, to discover new countries and to launch into exploration. And then now they are very important for international trade. Well, it seems that from all you said, there might be more important enough in 10, 20, 30 years as a hydrogen production distribution hub. So let's see what the future has for our ports and harbors, especially important in the UK and also in France. So thank you very much. Thank you, Philippe. Thank you, Pierre. Thank you, Hélène. Thank you, Paul. Jim had to leave a little bit in advance, but I thank him also. And now I will close that webinar. Thank you for the economic section, the science section at the embassy, and also for our partner Catapult and CUA. Thank you all. Thank you for this wonderful and very detailed insight, and we'll keep seeing what hydrogen has in store for us in the future. Thank you and have a good afternoon. Bye-bye.
Thank you very much. Goodbye.
Thank you.
Thanks a lot.
Bye.
Goodbye.
Bye.
Thank you.